think first. Okay. So hello again. So it's a pleasure to welcome colleague and friend Sandro Tacchella, who's a postdoctoral now, still fellowship, has a postdoctoral fellowship at CFA in Harvard. And before that, he did his PhD in ETH in Switzerland. Then, as I said, he moved to Harvard. And in a couple of months, he's moving for a faculty job in Korea. So congratulations on that. And Sandro is an expert on stellar populations and general galaxy formation, massive galaxy formation. And he has been working a lot on trying to understand how galaxies stop forming stars, essentially massive galaxies at high redshift transition from star forming to the quiescent state. And today is going to talk about, I think, one of his last works, precisely analyzing the stellar populations of high redshift galaxies, or at redshift 1-ish, and trying to infer star formation histories. So thank you very much, Sandro, and the floor is yours. Sandro, I cannot hear you. Maybe you are mute.
Okay. Sorry, yes, I couldn't change. Okay. So let me do that. Okay. So, well, Mark, thank you very much for the introduction and also for this opportunity to present some of my recent research. So I go over a few things related to star forming and quiescent galaxies at early cosmic times around redshift 1, 2, 3, basically. And if you have any questions, feel free to interrupt me or ask the questions at the end of my presentation. So I think the cosmic microwave background is really one of the key fundamental pillars of our cosmological model, the lambda CDM. On the left side, you can see the temperature fluctuation map obtained from the Planck satellite. And on the right, you can see the temperature fluctuation power spectrum. The red points are the observational data from the map on the left, and the green line shows you basically the best fit cosmological model, the lambda CDM model. And you can basically see that this looks like a great fit. And so I think we have overall a good understanding of the initial conditions for galaxy evolution already 380,000 years after the Big Bang. And so this standard cosmological model, as I said, the cold dark matter universe together with the cosmological constant, basically tells us that today's universe is really dominated by an elusive component called the dark energy. And then we have the matter component being dominated by the dark matter. And the ordinary matter or the baronic matter that we all know the best about is basically only about 5% of the total energy budget today. And so if we now, ask the fundamental questions such as how do we go from these small perturbations in the, the matter density field at early cosmic times to today's universe? We can see today basically a diversity of galaxies, roughly 14 gigayears after Big Bang. And my research interest is really understanding how does basically the universe evolve through this, this large time span and builds up such interesting cosmic structures as galaxies. And so, one of the key fundamental questions, how or what is our own place within this universe? And so for a moment now, we can maybe forget about the baronic physics and just focus basically on a cold dark matter only universe, right? A collisionless gas, basically. And if we do this, we can actually understand the overall structure of the universe quite well. So if we now use n-body simulations, we solve basically only for gravity and see how we go from the cosmic wave background, right, from early in the universe down to today's universe, we can produce maps such as here on the left, which shows you the dark matter distribution at redshift 0, so in today's universe. And you can basically see that the overall structure of the universe looks very similar to what we see when we look at the galaxy distribution. This is shown up here on the right. So galaxy redshift surveys, 10, 20 years ago, basically showed that we see that these filaments in the galaxy distribution, and this is very similar to what we see when we just look at the cold dark matter universe. And this basically, again, supports that we have a good understanding of the fundamental cosmological model. But of course, we still don't understand what the dark energy and the dark matter in itself is, but it at least reproduces the large-scale structure distribution of the universe. Now, if we look at more details of this model, we of course know that we cannot ignore the baryonic physics. And this is, for example, shown here in this figure here, where I show you the number density distribution of galaxies, the galaxy stellar mass function. And you basically see we have this power law at low masses, and then there's an exponential cutoff at higher masses. And if you compare this now to the dark matter distribution, right, the dark matter halo mass function, now this is rescaling basically the halo masses by the baryonic fraction. You basically see that galaxy formation or star formation in galaxies is very efficient, around 10 to the 11 solar masses, but there is inefficiency for building up stellar mass in low mass galaxies as well as in high mass galaxies. And so this clearly shows that we cannot ignore the baryonic physics, and galaxy growth needs to be somehow regulated. In particular, at high masses, we somehow need to suppress the star formation in massive galaxies, and this is what I will call quenching throughout my talk. We somehow need to suppress the star formation in these high mass halos so that we are not overproducing massive galaxies. You can see this also when you look at the stellar population. So, what is shown here is a U minus R color versus stellar mass. This observational data is from SDSS, and Kevin Javinsky presented this in his paper, where he basically corrected the U minus R color that is observed for dust. And so what you can basically see here is this blue cloud of star-forming galaxies and the red sequence of older quiescent galaxies. And again, this is kind of counterintuitive if you think about the cold dark matter universe, where we have galaxies building up from small structures to larger structures, right? So you would expect that the most massive halos are assembling most recently. But when you look at the galaxies, the most massive galaxies are actually the oldest galaxies, the most quiescent galaxies. And so this again says that, well, we have to somehow suppress the star formation in the most massive system, and then they need to basically age with cosmic time. So, how can we quench galaxies? How do we switch off the star formation in these massive galaxies? And so for this, I want to basically discuss a bit more what kind of baryonic processes are ongoing in galaxies. And here it's, of course, important to keep in mind the scales. So I showed you already this map of the overall dark matter distribution in the universe. This is, basically what we usually call the cosmic web. It's really, on the space, of gigaparsecs. Now, when we focus on dark matter halos, we already zoom in quite a lot, by a factor of, 1,000. So, dark matter halos are typically on, megaparsec scales. And then galaxies are really sitting in the centers of these dark matter halos, right? And have sizes of a few kiloparsecs typically. Now, of course, the overall structure of the universe is important for, thinking about like how galaxies evolve, right? There is a difference, we think, that, if a galaxy forms and evolves in a cluster or in a group versus kind of in the field or in a low density environment. But there's, of course, a lot of internal processes that also act in galaxies. And here we can think of, for example, star formation, right? That takes place in parsec scales. You can see here young, an obese association of stars that, somehow acts on the surrounding gas. And then, of course, we believe that in the centers of most galaxies, in particular of massive galaxies, there are black holes, supermassive black holes of, a few millions to a billion solar masses. And again, this is showing an image from the EHT collaboration. And this shows basically kind of the accretion disk of the black hole. And, here we're talking of very small scales where you can put the solar system basically in the central part of this accretion disk here. And so we're talking of like sub-parsec scales. And now, thinking about physical processes that act on all these scales, I put here down a few of those, right? We have black hole growth and black hole activity. And again, even though black holes are basically working on, or, basically act on small scales, there is a huge impact on larger scales by, for example, how black hole, the winds of black holes couple to the surrounding gas. At the same time, we have physical processes that act, for example, on molecular cloud scales. We have formation of stars in molecular clouds. We have supernova explosions and stellar winds. Then, stars, of course, have radiation fields that somehow act on the gas as well. We have the interstellar medium that is usually multi-phase, right? We have a cold phase, a warm phase, and a hot phase in galaxies. We have magnetic fields, which are largely still unexplored in galaxies. We have formation and fusion of cosmic rays that might be very important to understand how wind in galaxies are launched. And also we have gas flows, right? And cooling, this is on large scales, such as in the halo, but also on smaller scales within galaxies. And so you see this wide range of different physical processes that are acting on galaxies. And thinking now a bit more specifically about the quenching of galaxies, we can look at maybe a more simple picture of galaxies. So this is what we usually call the bathtub model or the regulator model, where we basically, think of a galaxy as having a gas reservoir that is sustained via some gas inflow. We have the formation of molecular gas, and the molecular gas then forms stars. And the stars, of course, they don't live forever, and somehow they will explode or lose mass, and so there will be some mass returned to the ISM, and some of this gas will also be being outflowing, right, with solar winds or feedback from a black hole. And so there are different versions of this model, and we have put forward one of these last year, where we looked at this in a stochastic sense, where we basically stochastically feed the galaxy and think a lot about how molecular clouds are forming as well. And here I want to just give you basically a broad overview of how you can stop forming stars, right? How you can suppress the star formation rate in a galaxy. And I will, give you a very rough overview here of some of the physical ideas. One thing is, for example, to prevent gas from accreting or cooling, right? You're kind of suppressing this inflow here. You can think of this as, cosmological starvation. You basically are in an environment where you have little gas available to cool. You can think of being in a hot halo, so you can suppress the gas accretion via thermal shock. You can heat the gas, via HEN feedback, or via gravitational heating, where you have basically gas falling in from the outskirts of the halo into the central part of the halo that will basically heat up through, gravitation. You can also prevent gas, cold gas, from forming stars. You can do this, for example, via morphological quenching, via a massive bulge in the center of the galaxy. An idea is, for example, to bar quenching or HEN feedback, as well as magnetic fields that suppresses the cold gas from forming stars. There is also other ways to basically, basically get rid of cold gas. You can, for example, rapidly consume this via mergers and disk instabilities that will then basically, destroy the gas reservoir, and so not able to form new stars from that. You can also get rid of gas, right? You can really basically push out the gas from the galaxy via HEN feedback or solar feedback. And you can see there is a lot of different processes, and some of them act on short time scales or on long time scales, and some of those also only act for a certain amount of time, right? You can think of, for example, you can consume all the gas very quickly, but then you can still cool gas later on, and so you have to somehow have also a maintenance mode to keep the galaxy quiescent. And of course, in the last few years, there have been a lot of numerical simulations, numerical models that try to solve for all of these processes, more or less self-consistently, with, of course, some subgrid models in them. And then there is a lot of, a wide range of different predictions from these models. And the question is, of course, why didn't we solve this puzzle yet, and why is progress difficult? And I think there are different, answers to this question. The first one, I think, is related to that these models made a wide range of different predictions, and prediction I put in quotation marks here because one has to be quite careful of understanding what has been done, to kind of tune these models to reproduce observations versus what is really a prediction from these models. And for example, when you think about the quiescent fraction, this is something that has been now basically tuned in these models in most of these numerical simulations that I show here at the bottom. But for example, the quenching timescale of how quickly the galaxies transition is something that is basically more predicted from these models and has not been put in these models. And so you basically see now, when you look at these predictions of how quickly galaxies quench or transition through the Green Valley, there is a wide range of different results from these models. And in part can be explained by actually using different quenching definitions, right? What is really quenching and how is it defined? And this is something that I will be touching on in the next few slides a bit more in detail. But you can see that, for example, in this work by Dylan Nelson from Illustrious TNG, they measure how quickly galaxies transition through the Green Valley as a quenching timescale. There is a work by Simba, from the Simba simulations and the Eagle simulations that use basically a specific star formation rate threshold. And you can see that then the results, quite different. There's also a difficulty now if you have these numerical simulations, right? How do we do a comparison to the observations? Because you want to do an apple-to-apple comparisons. And so somehow you need to make sure that however you measure certain theoretical quantities, you can do kind of the same kind of measurements in the observational space. And this is, again, a very difficult task and has not been done sufficiently, I think, until now. Then if you say, okay, let's forget about the models, right? And just focus on the observations themselves. There is, of course, a fundamental limitation also in the observational data and their analysis. So, for example, we cannot really observe how individual galaxies are evolving through cosmic time, right? The dynamical time scale of galaxies is large, and so we cannot see how a galaxy quenches, basically. We can see star-forming galaxies and quiescent galaxies, and the question is, how are these connected to each other? And so we have to do some assumptions there about evolving populations there. And of course, you can say, well, okay, let's look at quiescent galaxies and do this population analysis. And this is something that I will be touching on as well in my talk. But there, of course, a fundamental limitation is that we have mergers taking place. And so there's some kind of a dilution of what is really happening to an individual galaxy versus what has been happening to other galaxies that merge to this galaxy as well. And so these are some of the problems, I think, and that this is some of the reasons of why progress has been difficult. And so, as I said, I will be touching on most of this. So the key question I try to answer in the next, half an hour or so is really, how do galaxies basically leave the star-forming main sequence? So this relation of the star formation stellar mass that we see at all epochs, and how do galaxies basically cease their star formation? And what are the timescales for this quenching? And so I will first start by discussing really the definition of quenching. What do we mean with this? And then focusing on the first part, basically on redshift 2 star-forming galaxies, and basically try to see if we can see quenching in action. And then in the last part of my talk, focus more on the archaeological approach, so basically doing a population analysis of redshift 1 quiescent galaxies. And so why do we choose redshift 2 and redshift 1 to do this kind of analysis? And I think looking at the mass function is very telling. You can, for example, look at the key epoch around redshift 2, right, where we have the peak of the cosmic star formation rate density in the universe. We can see that the galaxy population is really dominated by star-forming galaxies, right? And the quiescent galaxy is still, the population of quiescent galaxies is still in a subdominant role here. But then already a few giga years later, around redshift 1, we see that the quiescent galaxy population has been growing very rapidly. And in particular, the high mass end is now already dominated by quiescent galaxies. So this already implies that a lot of galaxies need to transition basically from the star-forming population to the quiescent population. Also because you can see that the high mass end of the star-forming galaxy doesn't really evolve, right? If you would just integrate up the star formation, you would expect the mass function to evolve to the right here, as shown here by this green arrow. But the mass function, the knee of the mass function stays roughly at the same stellar mass. So this already also implies that quiescent galaxies need to build up because galaxies quench their star formation. So I think understanding quenching around redshift 2 to redshift 1 is really important, because that's where most of the galaxies actually transition at the high mass end. When we go to redshift 0, you can see that there is an evolution of the mass function at high masses, probably because of merging. But then when we go to low masses, you can see that there's suddenly this strong increase in quiescent galaxies. And this is something that is probably related to the environment and satellite quenching, something that I will not be touching on in my talk now. So let's first focus on the definition of quenching. And as I already kind of alluded to, I use a rather broad definition for quenching, which is really kind of the transition from being star forming to being quiescent. And of course, the immediate question is, okay, what do you mean with quiescent? And I refer to this as a state with negligible stellar mass growth due to star formation. And this is something that you can really physically write down, and thinking about the specific star formation rate, which is the star formation rate divided by the stellar mass formed previously, basically. And so if you solve this equation here, you can basically say, well, the stellar mass growth is roughly the previous stellar mass times the exponential of the specific star formation rate times the delta t, or rating, basically. And again, this assumes that the specific star formation is roughly constant. And so if you now ask the question, okay, how long does it take to double your mass or grow by an e-fold? You see that basically, well, you want to put this roughly to 1. So this means that the doubling time scale is roughly 1 over the specific star formation rate. And so now the question is, okay, when do you basically don't grow anymore due to star formation? You can basically say, well, this means that the mass doubling time scale is longer than the age of the universe, right? So if you wait and wait and wait, and so how long does it take to double your mass is longer than the age of the universe or the Hubble time, you know that you basically don't anymore really grow due to star formation. This means that you can still grow because of mergers or accretion of other galaxies, but you're not really growing anymore in mass, in stellar mass, because of star formation. And so this is basically the definition I will adopt throughout my talk. There are, of course, other definitions that are overall quite similar. You can think about simple color selection, right? For example, U minus V, V minus J, raster color selection. And this gives you to about a fraction of 10, 20%, a similar galaxy population. Star formation rate equal to 0 is, of course, something that can also be used, but it's something that is observationally basically not very feasible, because it's very difficult to basically rule out any star formation in galaxies. You always have some kind of upper limits. And this is something that you can see in the next slide as well. where I basically show the distribution of star formation in the overall galaxy population. So here I show you the specific star formation at stellar mass relation at redshift 0, at redshift 1, and redshift 2. And this is basically taking data from the Galax, Low, and Weiss, survey, basically measurements by Salim et al. And this is from 3D HST. And you basically see at all epochs this, these kind of upper limits here of quiescent galaxies. And so you shouldn't be thinking of like the same as with the color, mass diagram, where you can see this clear bimodality. These are basically upper limits, and we're not really sure if these galaxies sit here or whether they are kind of actually at lower specific star formation rates. So this is basically what we call the quiescent population at all times. And then you can look at the star forming galaxies, and you can see basically the sequence between the specific star formation and the stellar mass. And this has been coined the star forming main sequence, or the star forming sequence. So basically at all epochs up to redshift 3, we can see this relation between the star formation rate of galaxies and the stellar mass. Now, if we are using this definition I introduced before of the mass doubling timescale, you can actually draw lines of constant, specific star formation rates. And so what I show you here is basically a blue line shows you galaxies. So galaxies on this blue line are basically doubling their mass within a Hubble time. The galaxies on the orange line take already 10 Hubble times to double their mass, and the galaxies on the red line are taking about 100 Hubble times to double their mass. And so the key point here is that most galaxies down here, they are actually still having some specific star formation rate, probably, but they are not really growing anymore due to their star formation, right? They're already very massive, and the star formation rates are so low that these galaxies are not really anymore growing in stellar mass, and so they're not really moving anymore to the right in this diagram. And you can see this with these arrows that basically show you how much do you grow to the right if you would wait for a full Hubble time, right? If you wait for a full age of the universe. So if you wait today for 13.8 gigayears, these galaxies will basically grow all up here to the right. The galaxies here would only grow by this much, right? So it's very small basically. And so it's kind of wrong to think that galaxies have from here on the left are growing to the objects down here to the right, right? And you can think about this also when you think about the morphologies. We know that today's galaxies are, sustaining their star formation mostly in these galaxies, whereas the quiescent galaxies are early type galaxies with no spiral arms. But it's wrong, I think, to think about this in the sense of like that these spiral galaxies evolve into these ellipticals, because the progenitors of these galaxies here are really to be found at early cosmic times, right? We have to basically go to redshift 1 or redshift 2 to look at the progenitors of these galaxies that then basically form most of their stars, probably maybe in a different way because they start, the gas fractions were much higher and so on. And then basically transition to the galaxies to be down here. And so today's spiral galaxies are probably not the progenitors of the massive ellipticals. Okay, let's focus now on redshift 2, where we basically see the progenitors of some of these early type galaxies at redshift 0. In particular, we can look at massive star-forming galaxies because we know that those galaxies need to switch off their star formation very soon. And so we should be able to see some kind of quenching in action in these redshift 2 galaxies. And so how do we do this, right? So when we think about galaxies being growing on the star forming main sequence, on this typical average star formation stellar mass relation, this purple line I showed you before, we think the galaxies are growing in stellar mass on this relation. And I unfortunately don't have too much time to go into the details of how galaxies were growing on the star forming main sequence. I think the galaxies are oscillating around this ridge line of the star forming main sequence and building up their bulge component with cosmic time on that. And I've been recently quite interested to understand these fluctuations and describe this with a power spectrum. And I'm happy to talk more about some of the recent work I've been doing along these lines of how star formation is regulated. But now let's focus on these massive galaxies and think of how these are transitioning through the green valley onto the red sequence. And so I want to basically measure quenching timescales of how quickly galaxies are transitioning, because I think that if you are measuring how quickly galaxies transition, we will be able to learn more about the physical mechanism, right? You can think of if you destroy the gas reservoir, you're immediately quenching the galaxy, so you're basically quenching quite quickly. Whereas if you think about galaxies transitioning, slowly, it's maybe more to do with cosmological starvation, for example. And so in this forward approach, we hope to see quenching in action. But of course, it's difficult to then predict exactly the future, right? Do we really know that the galaxies are immediately quenching, or are they basically quenching rather slowly? And so let's focus now first on this approach, and later on, basically, turn it around and focus on the quiescent galaxies and see if you can connect back to the star-forming galaxy population. So here I've been working, back a few years ago and still working on some of the data using the Hubble Space Telescope. So I've been part of an adaptive optics SINF program that is together with MPE in Padua. And we have been basically, conducting the largest adaptive optics survey of redshift 2 galaxies using spatially solved spectroscopy. And I've been leading the Hubble Space Telescope follow-up of this program, where we basically took images such as those, and we are focusing on these galaxies here. For example, this is a redshift 2 galaxy, and this is a color composite from Hubble images using V, I, and H band. This is rest frame, near UV, far UV, and optical. And as I said, it's an adaptive optics symphony survey. So we basically get also H alpha maps of these galaxies using the K band. And so this means that basically for each individual pixel, we get a spectrum where we can trace the H alpha emission line, which is of course a great star formation indicator because it traces the ionized gas. And because we are able to do we basically get the emission line, we can also look at the Doppler effect and basically measure the velocity map of the H alpha emission line. And you can basically see this here. So we can not only get the flux distribution, but also basically the dynamics or the kinematics of these galaxies. And so what did we learn about this? So using basically H alpha as a star formation rate tracer and the HSD images as a stellar mass tracer, we can actually map out the star formation distribution in these rather young galaxies. And I'm focusing now here just on the most massive galaxies in our sample, around 10 to the 11 solar masses. And you basically see that star formation distribution, here shown in blue, is typically described by an exponential disk, whereas the solar mass distribution is much more centrally concentrated and with a Sersic profile of n equals 3 roughly. And so this means that we have solar mass densities in the centers here that are very comparable to local early type galaxies actually, of several times 10 to the 10 solar masses per kiloparsec squared. And so if you now look at the specific star formation rate distribution as a function of radius, right? So this is again the star formation rate density divided by the solar mass density at all radii basically. You can see that the lower mass objects in our sample, like Milky Way mass at redshift 2, right, have roughly flat specific star formation rate profiles. And so this means that these galaxies are roughly doubling their mass at all radii self-similarly, right? They're basically solar mass density is kind of growing self-similarly, and we have a mass doubling timescales of roughly 300 million years. So these galaxies are really rapidly growing at all radii. However, when we look at the most massive galaxies in our sample, we can see a suppressed specific star formation rate in the cores of these galaxies. And so basically what this means is that they have a lot of solar mass already there, and the star formation activity in comparison with the solar mass there is kind of negligible. And so you see that here basically we have a quiescent center, so we have these dense bulges, and then we have basically a rotating star forming disk around them. And so we put forward basically this idea that galaxies are quenching from the inside out, and that you're building up these dense bulges on the star formation sequence at early times, and then you are quenching the star formation from the inside out, and you're producing a typical early type, M-star galaxy that has a lot of rotation still. And of course, if you go through a merger, you might end up ending, more massive as well as being more, spheroidal and more dispersion dominated. Now, the question is still, of course, how do these galaxies quench? So we say like, okay, well, they quench probably from the inside out, but what's the physical cause for this at these early times? And I want to just give you a kind of how do we estimate these quench of these timescales? And here I maybe just want to show you a movie, and this is maybe shown best here. So the red line here basically shows you the stellar mass density profile. The blue is the star formation rate profile. This is what we measure at redshift 2. And the dashed line here shows you the typical solar mass density profile of early type galaxies in the local universe. And you already see that, we have a lot of solar mass already made in the central core of these galaxies. So we cannot grow for a too long time in the centers. On the other hand, we have still, more time to grow in the outskirts. And so if you now just integrate up the star formation distribution, you basically see that you have to quench the star formation from the inside out. And, we can estimate a rough timescale for this. Sorry, now I pressed the wrong button. So let me just share the screen again. But let's go back to the slides. Okay. So what's the timescale for this inside out quenching basically? Okay. So we can, get basically a timescale of a few hundred million years in the central core, so they can only grow for a short amount of time, and then later on they can maybe form stars in the outskirts for another 2 or 3 gigayears, right? And important, this ignores basically stellar mass contribution from like minor mergers in the outskirts. So this is something more like an upper limit. So what quenches galaxies from the inside out? And I think the question, of course, is it related to the black hole feedback? And I think we have quite intriguing evidence for this. When we look at the H-alpha emission line, we can actually do a decomposition of the emission line profile into a narrow versus a broad component. And, this shows you basically the full width half maximum of this, broad versus narrow component. And we find that when we go to the most massive galaxies in our sample, there is clear evidence for a broad component in the H-alpha, emission line shape in the central part of these galaxies, in the central 1 to 2 kiloparsec. Whereas when you look at the disk component, even for these massive galaxies, there's not really an evidence for this broad component. And so we measure full width half maximum of 1,500 kilometers per second. And so we think that these outflows are really not driven by star formation, but more by a black hole. Now, what else did we learn from? So what do simulations say about these, this kind of inside-out quenching scenarios? And so in a recent paper, we looked actually at illustrious TNG, and we came to the conclusion that we see a similar shape in the specific star formation profile in these simulations. We see the galaxies are quenching from the inside out. And in these simulations, it's clearly that it is due to the black hole feedback, right? So the black hole basically blows out the gas in the central core and suppresses the star formation activity in the course of these galaxies. On the other hand, when we look at other simulations, the VILA simulations, for example, we can find a similar quenching, timescales going from the inside out. We basically actually see that this can also be sustained not by an HEN feed, but it actually can be done by a stellar feedback alone, and somehow making it inefficient for the gas to accrete into the central core. And so you see that even when we look at different numerical models, they seem to be consistent with some of these observational signatures that we see. But it's not clear whether this is really driven by an HEN feedback, at least, when we look at these simulations. Okay, so let's now focus on quiescent galaxies and basically see where galaxies are already quenched, right? So we go basically in this look-back approach. And the good thing here is, of course, we know that quenching happened because the galaxies are quiescent. And so we can maybe estimate the quenching timescale by measuring the star formation history in great detail. The problem there, as I mentioned already at the beginning of my talk, is that there is a mixing of in situ, so basically the stars that form within this main progenitor of the main galaxy, and the accretion of smaller galaxies that maybe mix up the stellar populations, that maybe quench at a different time scale, and so maybe inhibit some of the main conclusions of this kind of analysis. So I think this mixing of the in situ and ex situ component is something that we have to keep in mind in the next few slides when I go to some of the conclusions of my result as well. So here I've been using the HALO7D survey. This is led by UC Santa Cruz, basically. And it's basically a collaboration of people who really study the Milky Way halo and us, the galaxy evolution people who are interested in the background galaxies. And so the main idea of this survey, as the name says, it was about the stellar halo. So basically measure stars in the Milky Way halo with JWST to get the proper motions, and then using Keck demos to get metallicities, and a line of sight distances and so on. And so this is really focusing on stars, but we had many filler galaxies in the background that were all lying in the Candles field. And so we have these very deep exposures, of 8 to 32 hours of integrations at Keck. And we basically have these two samples of low and high mass galaxies that we are currently analyzing. And I've been focusing on this high mass sample that really focuses basically on redshift 0.8 to redshift 1 onto the massive end. So basically around 10 to 11 solar masses, we have an unbiased sample in polar. So we basically have both star-forming galaxies and quiescent galaxies. But then when we go to lower masses, we selected specifically quiescent galaxies. And so again, this is not a mass complete sample in that sense, but it is basically a polar unbiased sample when we go to the massive end of these galaxies, and then focusing really on quiescent galaxies at lower masses. So we have roughly 161 galaxies with a signal noise of more than 5 per angstrom for all these galaxies. And what I've been working on is in the past few years, working on Prospector, which is an SSD fitting code that is fully Bayesian. And it allows to rigorously combine basically the photometric observational data with the spectroscopic data, right? So we don't want to just focus on the spectroscopic data alone and the photometric data alone. We really combine all of this together and really see what do we learn from this observational data. And so the model that I'm fitting, basically, the physical model that I'm fitting to these spectrum photometry are quite complicated. It's roughly a 20 to 30 parameter model. It has standard model parameters such as redshift, stellar mass, velocity dispersion, and metallicity that we usually assume in these ACDM model approaches. But then there are also more flexible things such as the flexible dust attenuation law, where we have the amount of attenuation, but also the attenuation law itself is a free parameter. This is important if you want to interpret the UV, with the solar ages, as I will show you in a few slides. And then we have the dust emission, because we want to also basically fit the 24 micron MIPS. So we have to have a model for the dust emission, as well as HEN emission in this wavelength range. Very important for measuring quenching timescales is to have an idea of how to measure star formation histories. And here I'm using non-parametric star formation histories, basically, where we have 10 bins in time, and we're letting them free to vary so that we can understand the shape of the star formation history and constrain the shape of the star formation histories. We also have, emission line model fitting part in our model. This is important because we believe that some of the emission lines are not just star formation, but actually maybe liner-like emission. And so we have to have this as a flexible tool as well. And what we do is basically fit for the velocity dispersions consistently, but optimize out the amplitudes. And then we also have an outlier model to take into account that we don't perfectly, sky subtract, there are probably some skyline residuals or detector artifacts that we cannot fully model. And so again, I don't have time to go into the greatest details. I described this all in my kind of recent paper, and it has a long appendix. And I basically discussed quite extensively that the priors are very important. So in this Bayesian approach, you have to make sure that you have a good understanding of your priors and how this maybe affect your posteriors and your main conclusions of the paper. And this is something I don't have time to go into the greatest details in my next few slides, but if you're interested, I'm happy to discuss this more, after my talk, or, there's a lot of this also, of course, in the paper. And so I'll show you here one of the example galaxies. So this is basically a photometry that we're fitting. It goes all from the UV to the optical and to the near infrared. And this is the spectrum, right? And why is it important to fit both? Again, the spectrum covers quite a narrow range in wavelength. And so we are not able to, for example, measure the dust attenuation very well from the spectrum itself. And we basically want to have the photometry to constrain the overall shape of the ACD. And so putting this together, we can now, I'll show you here some posterior of typical parameters as mass, specific star formation rate, dust, age, and metallicity. And as I said, we have this flexible star formation history so that we are able to get the shape of the star formation histories for each individual galaxy. And for example, this galaxy here, they had a kind of, continuously rising star formation at early times, had a plateau, and then, quenched in the past year or so. And so we can do this for all galaxies. And I was just going to highlight, why do we want to choose non-parametric instead of parametric star formation histories, right? So one of the typical star formation histories that we assume is usually this delayed tau model, where we have basically kind of a slow build up at early times and then quite a rapid decline of the star formation by an exponential decrease. And you can see that, at recent times, these two approaches are very similar. And this is because that's where most of the signal to noise is. So, the model really want to agree there. But then when you basically give this shape as given, right, in this parametric approach, you don't have really a possibility to get this older component here, right? And so you basically, start your star formation quite recently, and this leads to a different age, basically, which then also leads to a different mass, right? So you get these kind of more biased quantities, basically, out if you assume a kind of a very strong parametric shape in the star formation history. The question, of course, is also what do we gain by including photometry and spectroscopy in the fitting and not just doing spectroscopy or photometry alone? And, there are these general things that we all learned about, I think, is like, okay, sure, if we just look at the spectroscopy, we cannot get a good, constraint on the dust and the mass. But for example, the age is quite well constrained, as well as the metallicity. If you include the photometry and only look at the photometry, we actually are able to get the mass very well, but and the dust overall, but we have only limited amount of information we can get basically when we look at the metallicity. And so in the star formation history and the age is actually quite different, kind of interesting, right? If you look at the photometry, you say like, well, the galaxy is actually quite old. if you just look at the spectroscopy, you say, well, the galaxy is actually slightly longer. If you include both of those, you see that the age is actually in between. It's not just sitting on the spectroscopy. And this is because the star formation history has a lot of constraint also from the photometry, in particular in these intermediate age constraints that come in from the UV. So you see that at early times, you basically agree with the spectroscopy, and then you're in between, but quite close to photometry. And at the end, you're kind of in agreement again between both of those approaches. And this is again basically telling you that the UV has a lot of constraints on the ages, and has basically information on stars, all from a few tens of million years up to a giga-year basically. And so that's why we want to include the UV information in the star population analysis as well. And the dust attenuation there is of course very important. That's why we also have this flexible attenuation, so that we can marginalize over different attenuation laws basically at the same time. And so the key result from this analysis is basically that we have this wide range of measurements for the star formation histories, and then each individual diagram shows basically the specific star formation versus look back time. And again, basically galaxies up have high specific star formation rates back in time. They are all star forming. We have this transition regime defined by the Hubble time, and then galaxies basically transitioning through the Green onto the quiescent sequence. And so this just shows you that basically the galaxy sample split as a function of cosmic time, the redshift of observation, and as a function of mass. And you can basically zoom in on one of these diagrams, and you see basically that we see this large diversity of pathways, right? There are still some overarching features. So for example, when you look at the star-forming galaxies, we see the specific star formation rates of the star-forming galaxies in our sample. They actually follow very well back in time what we measured directly for the star-forming main sequence. So this means that galaxies are typically following the star-forming main sequence on average. And they also follow this specific mass accretion rates of the dark matter halos shown by this gray band. So it seems that the measurements that we get out are very sensible if you look at direct measurements at earlier cosmic times. Focusing on quiescent galaxies, you see that they're transitioning, and it seems there is not a strong mass dependence on how quickly galaxies quench. It seems that more massive galaxies typically quench slightly earlier on, and back in time, right, roughly around redshift 3, they seem to be on the star-forming main sequence and basically decoupled afterwards and be quiescent, around redshift 1. So let's focus on quiescent galaxies a bit more. And again, the key conclusion from our analysis is that we have this large diversity of quenching pathways. We have galaxies that quench very early on, and we have galaxies that quench very late, even though they are roughly observed at the same redshift and are all high mass, right? So it's not that all high mass galaxies quenched early or late, but there is this large diversity in when galaxies quench, so the quenching epoch. But at the same time, you can see that there is this large diversity of how long it takes for galaxies to quench. You see galaxies sometimes quench very rapidly, and sometimes galaxies quench very slowly. And so we can focus on this a bit more and define the quenching timescale, the time between of how long it takes to transition through the green valley, basically between these 2 points. And so we can measure this for all the galaxies in our sample. And what is shown here is the observational data, basically. So we see here the quenching timescale as a function of the quenching epoch. And these are all the galaxies in our sample. And we see, again, this diversity of like some galaxies quench early, some galaxies quench late. And again, there is basically a lot of timescales involved, right? So in galaxies that quench between redshift 1 and 2, some of those galaxies quench very rapidly, something similar to what we maybe directly see as post-starburst galaxies, and then some galaxies that quench quite slowly. Now we can do the same exact measurement actually in illustrious TNG. So there I've been basically taking the star formation histories of illustrious TNG galaxies around redshift 1 and projected them into the observational space, predicting the spectra, the photometry, adding the noise as we see them, as we do this in the observations, and then basically reprocess it with the same machinery. And what we see is basically that typical quenching timescales and quenching epochs are similar, but we don't see these outliers, right? We don't see these very slowly quenching galaxies or these galaxies that quench very early on, which might show that the quenching pathways are too narrow in illustrious TNG, and so the quenching mechanism may be too simple. But I don't want to overinterpret this result because, again, outliers are prone to cosmic variance and so on, right? These rare objects are prone to cosmic variance. And again, we don't have a mass complete sample in the observational space. So one has to be a bit careful there. So, but what could be, a possible quenching mechanism that produces such a large diversity of quenching timescales, right? And so here I want to make the point that it has to be with a combination of an internal process or processes and an external process. And so what do I mean with this? Again, going back to the diagram I showed you kind of earlier in my talk, and I think about galaxies are growing on the star-forming main sequence, right? This is a function of halo mass now, but you can think about stellar mass as well. And around 10 to the 12, galaxies are entering typically the hot halo, right? Where basically the gas is very shock heated and the accretion rate of gas and cooling is kind of suppressed. And galaxies seem to be not accreting that much amount of gas anymore. Now, if you have now two galaxies, that are basically growing on the star-forming main sequence, right? They're kind of oscillating probably. They are maybe going through a merger or a gas compaction phase induced by, violent gas instability. And basically up here, we can think of having like this starburst phase, right? Where a lot of gas gets consumed. So you can think that maybe all the gas in the gas reservoir gets consumed on the top of the star-forming main sequence. And the question is now, when is this happening, right? Is this basically when you're still in a cold halo, when you're still accreting gas, or is this already happening just after you're reaching a hot halo? And so in a model, in a galaxy where you basically are consuming all your gas, or going through a merger where you consume all the gas in a hot halo already, you're not able to replenish the gas, right? And so basically the replenishment time is longer than the depletion time. And so you're immediately kind of, running out of gas and you're quenching quite rapidly. On the other hand, if you go through this gas consumption phase, when you are in a cold halo, you can still accrete some of the gas. And so the replenishment time is shorter than depletion time. And so you're kind of suppressing your star formation, but you do this quite slowly because you're still, having some gas. And so this means you're quenching quite slowly. And so you see that there is this idea of having an internal process, which is maybe related to the black hole or stellar feedback to consume your gas and or push out the gas as an agent. And then you have dark matter halo as a gatekeeper. And depending on how these things line up in time, you might quench fast or slowly. So again, I just want to use the last few minutes to discuss a bit more the star-forming galaxy population. And here, we can track galaxies basically back in time from the star formation histories and see the quiescent galaxies move back onto the star-forming main sequence. We actually can measure the star formation histories also for our star-forming galaxies, right? Which I kind of ignored, in the last few slides. And we see that those galaxies actually seem to have some variability in the star formation history in recent times. Again, supporting this idea that galaxies are not always above or below the star forming main sequence, but seem to oscillate. And then we can also have, rejuvenating galaxies, which are only a small fraction in our sample. But those galaxies, interestingly, all had, a very early star formation, were quiescent, and then had, a rejuvenation event quite recently. And so you see that when we go back in time up to redshift 3, they have not been really fully back on the star forming main sequence actually by that time, as for some of our quiescent galaxies, or most galaxies are actually able to go back to the star forming main sequence. So I think I'm running out of time. Maybe I have another 5 minutes or so. Mark, I don't know, but
yeah, I think it's fine if you take 5 minutes more. It's okay, no problem.
Okay. So, one thing that we can just look at the basic points is, when do the galaxies form most of the stellar mass, like the formation redshift, which is like the redshift when 50% of your stellar mass was formed versus stellar mass. And again, if you just look at the whole sample, right, as a formation redshift versus mass, you see this large diversity of formation redshifts. And this is now all the galaxies that are forming and quiescent galaxies. And this is consistent with what other people have found. And this figure is a bit confusing, but there is a lot of other measurements. There are slight differences between these measurements. I don't have time to go into the details. But one thing that I want to stress is actually quite interesting that there is this population of very massive galaxies that formed very early on, right? These galaxies formed their stars around redshift 6 to redshift 10. And we have direct evidence also for quiescent galaxies at early times. So it seems that these galaxies are very interesting to study with JWST because it seems that some galaxies are really forming very early on in the universe. Now, there is still some interesting trends. And one thing that, is not too surprising, I think, is that the galaxies that form these, very early on, they also have short star formation timescales, right? They are forming their stars, a few tens, a few hundred of millions of years, less than a giga-year, basically. So they have very rapid short star formation timescales, and then basically seem to suppress the star formation activity. And so for the next few years, what's ahead of us, and basically touching on some of the topics I was discussing in my talk, of course, I'm very interested in the spatial resolution of galaxies, right? And we can learn about the star formation process on spatial resolved scales in galaxies around cosmic noon. But the other thing is that we can really start understanding quiescent galaxies and do stellar population gradients in galaxies, which will really tell us of how quickly galaxies are basically quenching from the inside out. I'm of course very excited by the James Webb Space Telescope, which will be launched later this year. As you all know, it's a major mission, and I'm part of the NIRCam GTO team, and we'll be conducting one of the largest galaxy surveys at early cosmic times. And you know why JWST is so cool, right? It's because it has large mirrors, you can collect more light, but you also have a lot of more sensitivity in infrared in comparison with Hubble. And so this will basically lead, you know, when you think about, 1 to 4 micron images, currently with Spitzer, we are kind of, really confusion limited. With JWST, we're able to, spatially resolve galaxies and really find the faintest galaxies in the universe, which will help us to not only find the earliest forming galaxies, but also able to characterize them in much greater detail, in particular in this crucial epoch of reionization. And I'm here very interested to basically understand, with the stellar population analysis, when did the first galaxies form and basically dark ages end, which serves as reionized universe, right? The stellar population. I mean, galaxies are very important for understanding this question. There are also interesting questions related to the bulge and disk formation that I didn't really touch much on, I think, but I mentioned to you that at redshift 2 we already see very, very strong central densities, basically high central densities, and so it seems that the bulge components form at very early cosmic times, and JWST will be able to tell us more about this beyond redshift 3, because we can measure the rest frame optical. And we can do very basic things like measuring the stellar mass, distribution in the galaxy population, which helps us to constrain the stellar to halo mass relation. And current numerical simulations predict a wide range of different models that basically a wide range of different relations. And so getting some handle on just the stellar masses of these early galaxies, I think, will be very telling to constrain some of these feedback processes in these simulations. And so if you're interested in JWST, I'm currently really focusing a lot on the data reduction, the mosaicing, and the photometry and source detection. So if you're interested in this, I'm happy to talk about this also offline from my talk. We are currently developing a source detection algorithm using a deep convolutional neural network, working on a GPU-based photometry tool. We basically forward model all the images. And here we want to use just the mosaic to do the source detection, but then basically do the photometry measurements and the individual exposure so that we don't have to worry about the correlated noise that you have when you do the mosaicing basically. Okay, so conclusions. As I said, I showed you that star-forming galaxies at early times seem to quench from the inside out. This might be related to the black hole feedback. And then at redshift 1, we already see a large diversity of galaxies in place. Galaxies seem to transition through a wide range of different quenching timescales and quenching epochs. And there's, of course, a lot of more going on when we go to redshift 0, which I didn't really touch on, whether you go into a fast rotator or a slow rotator regime, depending probably on environment to some degree. And as I mentioned to you, I think I'm very excited about the future, thinking about the James Webb Space Telescope to constrain the formation of the first galaxies, the first quiescent galaxies. And I think there's a lot of potential to understand more on how quickly galaxies transition, because this tells us more about the quenching mechanism, as I mentioned to you in my talk. And I also think that there must be more careful comparisons between observations and theory. Some of that I showed you basically to project the simulation, the simulation quantities into the observational space and redo the same measurements as we do with observations. So yeah, that's all that I had, and thank you very much for tuning in and listening.
Thank you very much, Sandro. That was exciting. Do you have any question? You can type it in the chat or just, raise your hand. Go ahead. Don't be shy. I have one in the meantime. I have several, but one. So it's pretty interesting when you compare the quenching timescales with illustrious TNG. And I was wondering if you can establish more conclusions, because in TNG, the quenching is exclusively black hole, right? It's the kinetic feedback from the black hole that quenches all galaxies, essentially. So the fact that you don't see these other objects, so does that mean somehow that there's something else than the black hole? Or you think you can implement still differently black hole feedback and still get these, diverse quenching timescales?
Yes. So that's a very good question, and I think, you know, like, first of all, you could conclude that, but I'm very hesitant to already blame the subgrid model in these simulations, just because the simulation, the resolution in simulation is also a problem, right? So you see, you can maybe you are underproducing these early quenching galaxies in the simulation because you have maybe a too small volume you're studying, because they are rare in the universe. But actually, the volume between our observations and the simulations are actually quite similar. So if you ignore that, you can still say, well, maybe it's because of resolution, right? Before you're tuning the subgrid model, maybe you have to run a high resolution simulation. So for example, TNG 50, right? Because I used, TNG 100 here. And so maybe with TNG 50, things would look different, but there it's even a smaller volume. So it's actually, there is a problem of just saying, well, it's just a subgrid model, because the resolution itself might be an issue as well. Beside that, I think there seems to be a lack of early quenching galaxies in the simulations. But you see, there is also an issue of what happens to galaxy at a later stage, right? You can still quench a galaxy maybe in the simulation early, but then maybe you're rejuvenating them too efficiently, right? Maybe with the gas, like maybe when satellites come in that are on a very good resolve, you have gas in them, and then you basically quench these, and you bring new gas into these galaxies, and you're inducing star formation. So again, there is maybe a confusion between the in situ and the ex situ mass. So there are, I think, at the moment for me, a lot of more questions than answers. And so I think one thing to focus, for me at least, on is also understanding how well does the star formation history of the stellar populations really track the star formation history of the, when you look at the galaxies in the cosmological simulation, for example. And the answer there, the first order answer that I found until now, is that actually the agreement is quite good. So the star formation histories of the ex situ stars, when you look in the galaxy, is very similar to the in situ stars, actually. So there is some kind of coherence length scale in the universe there, which is, I think, consistent with some of the low redshift studies that showed that as well.
Okay. Someone has another question. Please, no? I can keep asking questions. No, so it's when you, the inside out quenching. So at some point I was thinking how you could distinguish this from, a bulge that is formed very early and then accreted disk. So can you comment on that?
Yes. No, I mean, I agree that you would want to understand maybe the cell populations better, right? In more detail. And I think things are consistent with having, I talked about that the star formation is not constant sustained through the whole universe, right? Like you have this fluctuation. So you can think of this like indeed having maybe formed this, this object here is quite massive, has a very dense bulge, and then has somehow, you see, when you look at the, it seems like there's a lot of rotation in this component here, right? That, it's maybe even reaccreted gas, and that's something that we cannot rule out at the moment. So if you look at these objects, they maybe had, an episode of very little star formation in the past, and then, accreted gas, and are now basically forming most of the stars in the outskirts. And so that's why I said, like, it's not very clear whether these galaxies are really, pushing out their gas and basically suppressing the star formation and quenching, or whether this is like maybe somehow, went through an episode of low star formation and now reaccreted gas that is not able to really penetrate into the central part of the galaxy and maybe stays more in the outskirts where it forms happily its stars. And so that's why I say, like, it's, when we look at simulations that have no HN feedback, they actually reproduce very similar trends when you look at the specific star formation rate profiles. And so we could, introduce this also without a strong quenching agent, right? And there are, on the other hand, other simulations where you really need a strong quenching agent to make that, right? And so that's why I say, like, it's from the simulation side, from the theory side, it's not very clear what we need. And that's interesting, right? Because it's like an unsolved problem there. On the observational side, as I said, like it's difficult to interpret as well, just because it's consistent with different kinds of simple scenarios, basically. Yeah. So as I say, like what we see is high central mass concentrations, and we see this component that is exponential, and whether this has to do with flowing gas out in the core or not is debated, I think. again, we found these powerful nuclear outflows. So for sure, there is some kind of a nuclear outflow in these galaxies. So there is something going on there. But whether this is really, again, correlation doesn't imply causation, right? Whether this really is where the question of confirmation is, we don't know. And that's why I think it's important to look into the theory space as well. Even though as an observer, we usually say, well, you cannot trust the simulations. I still think in order to solve this puzzle, we really have to, go hand in hand in some sense with the numerical models to understand, how the different implementations result in different observational points.
Yeah, at this point, however, so you said we will have lots of new data, but can you think of any measurement that we can do to break these degeneracies? Because you can have deeper spectra than what you have there, but at the end, I don't think this will, or maybe more statistics. But yes, it looks like a very degenerate problem, right? So.
Well, exactly. So that's why usually that's why in the last few years I moved to star formation and star formation variability and so on, because I feel like there, some progress can be made. Here, I think progress can also be made, and I think there are different avenues, and I highlighted them very, very quickly, right? I think, understanding the cell population of the first quiescent galaxies, I think is maybe telling us something of how quickly galaxies quench. Because the closer you are to the quenching epoch, right, the better you can resolve the quenching timescale, and the less you have to worry about mixing of ex situ and in situ. So you want to really go to higher redshift. So JWST would, give us some constraints on that. And also, space resolve it, right? There are, I'm part of some slit stepping experiments, and so I think we will get some age gradients, even if they're very rough. But I think there is some way to make progress. There is some, way forward with, HST is also like they do lensing, right? Quiescent galaxies. I think there are first constraints on star formation history and spatially resolved scales. And something that I didn't touch on is actually the abundances, right? And this is something I'm working on at the moment, is the metallicity, but also the alpha abundance, the alpha to iron ratio, basically. Something we can start constraining in these spectra and also on spatially resolved scales. And again, this tells something of how quickly these galaxies form their stars. So I think there is some, more constraints on the star formation timescale and how quickly galaxies are transitioning. And I really think that if you have more constraints on the quenching timescales, this will help us to constrain numerical models, I think. Yeah, because as I say, like, I think in the VLA simulations, right, where there is no HEN feedback, galaxies quench very slowly and they don't fully quench actually. So they still have some residual star formation, even though, like 1 dex below the star formation sequence. Whereas simulations as illustrious TNG, they quench typically quite rapidly. And as I said, they are maybe doing this with a black hole feedback. So, taking these simulations and basically projecting them into these observational spaces and doing the apple-to-apple comparison, I think will tell us more about the quenching timescales, and about the quenching mechanism. But again, I just want to caution that it's probably not just this one thing that quenches galaxies, because I think that we see this diversity, and this diversity might imply that different mechanisms act kind of together, and they might act kind of complicated together, depending on what happens first. And so you might end up with a diversity of quenching histories with actually, two processes that are kind of acting in some way, but it's maybe not too coherent.
Okay.
Can you still hear me?
I can still hear you. Can you hear me?
Yes, I can hear you, but my computer froze. So
yeah, I see that your image is frozen. So okay, so I think it's a good time to close the session then.
Just talk and not show slides anymore. Yes.
Yeah, but anyway, I'm not sure if there's questions. Otherwise, I think we can stop here. And thank you very much, Sandro. And I'll hope to see you soon. And good luck with everything that comes.
Yeah, thank you very much for inviting me, and yeah, I'm happy to answer all the questions via email or so.
Yeah. I mean, it's just yeah. Okay, I'll let everyone know.
Thank you very much. Yeah.